AWS says their Graviton 4 processors deliver 30% better price performance than the previous generation. That claim is completely real and mathematically flawless inside the strictly controlled testing environments AWS uses to generate it. But those pristine lab conditions tell you almost nothing about how that processor will handle the chaotic, unpredictable traffic of your actual production workload. No spec sheet can answer that. The core friction in cloud spending is organizational. The engineers designing the architecture and selecting the instances make their decisions weeks before the finance team ever sees the resulting cloud bill. Because of that delay, companies fall into a trap. They evaluate the success of an engineering migration by looking at the total monthly infrastructure spend. Infrastructure cost alone is a terrible feedback mechanism. Consider a team that doubles their monthly cloud budget but successfully triples their system's overall throughput. That is a massive operational win. They improved efficiency, even though the bill went up. The negative inverse happens constantly. A team cuts their monthly bill, which makes the quarterly financial review look great, but no one notices that the degraded system is now producing far less work for every dollar spent. Asking, "How much are we spending?" leads you to the wrong conclusions. A total dollar amount simply cannot distinguish between a highly efficient operation and a degrading system. To optimize for the right outcome, you have to replace total spend with a new metric, cost per operation, or cost per unit of work. This animated diagram breaks down the new formula. The numerator is straightforward. You take the total spend for Amazon's Elastic Compute Cloud, or EC2, for a specific service over a defined time period. The denominator is what actually matters. You divide that spend, the actual work the infrastructure produced. For an API service, that is the request count. For a data pipeline, it is gigabytes processed. For AI workloads, it is the number of tokens generated. A token is a basic unit of text, like a syllable, processed by an AI model. The math reveals the truth. If your denominator, the work produced, scales up significantly faster than your numerator, your true infrastructure cost drops sharply. Efficiency improves even as the total bill rises. Whenever a team changes instance types, tracking this specific ratio is the only definitive way to prove whether the architectural change actually helped the system. Hourly cloud pricing is exactly like the price of a gallon of gas. It is a baseline expense. Your true operational efficiency is your miles per gallon, how far that single unit of fuel will actually take you. The unit of work you place in that denominator dictates exactly what your engineering team optimizes for. It forces the focus away from arbitrarily cutting budgets and directly toward maximizing system output. That focus on output exposes a major trap in how teams select their compute architecture. Right now, there are three main players: Intel as the legacy default, AMD as the aggressive challenger, and Graviton shifting the economics entirely. ARM processors are designed specifically for high efficiency and lower power consumption. This comparison matrix shows the sticker price illusion. Current on-demand pricing positions Graviton up to 15% cheaper per hour than comparable Intel instances. But if an Intel instance processes 30% more requests per hour for your specific workload, Intel's cost per request drops below Graviton's. You pay a higher hourly rate but get a better deal on the actual work. AMD offers its own exception. For compute-intensive jobs heavily reliant on floating-point operations, complex mathematical calculations involving decimals, AMD's throughput often surges. That allows it to win the cost per operation race despite costing more per hour. The cloud vendors will not highlight these discrepancies for you. AWS benchmarks each new instance generation strictly against its own predecessor. They ignore cross-architecture comparisons. AMD does not even appear in Graviton marketing materials. Relying on spec sheets hides the true competitive landscape from the buyer. Migrating workloads based solely on the cheapest hourly rate guarantees you are optimizing for the wrong metric. It leaves you entirely blind to your system's true performance. To fix this blindness, teams must run their specific workloads across all three instance architectures before pushing any migration to production. These tests must simulate realistic load. That means mimicking the cruising speeds where the system spends the majority of its day, not just the maximum peak bursts. This decision flowchart lays out the mandatory measurement loop. Simulate production load, record your primary unit of work, divide that number by the hourly instance cost. Finally, select the lowest resulting ratio. While Graviton often wins this test for general-purpose Linux services, its superiority must be proven as a hard finding. It cannot be assumed as a premise. Dedicating the upfront engineering cycles to run these benchmarks is your only legitimate defense against compounding financial waste as your infrastructure scales. Once benchmarking identifies the most efficient processor, you can heavily compound your savings using the commitment layer. You do this through Compute Savings Plans, a flexible AWS pricing model offering lower prices in exchange for committing to consistent compute usage. This stacked bar chart demonstrates the math. A 1-year Compute Savings Plan stacks directly on top of Graviton's base economics. That drops the effective rate up to 44% below an Intel on-demand instance. Compute Savings Plans are far superior to traditional reserved instances. Reserved instances lock you into a specific instance type and geographic region. Savings plans provide flexibility across different EC2 families, regions, and even serverless compute engines like Fargate. But you must right-size your instances before applying a savings plan. Committing a plan to an oversized, underutilized instance is just locking in financial waste at a slight discount. That right-sizing process contains a dangerous trap. Many teams will shrink an API tier to a smaller instance simply because their dashboards show a low, safe, average CPU metric. Look at this line chart. A flat average CPU completely masks your P99 latency. P99 latency represents the slowest 1% of your system's responses. When those extreme, momentary traffic spikes hit, the smaller instance violently runs out of headroom. The damage is hidden from the finance team. The monthly infrastructure report looks flawless, while the end user experiences unpredictable, hard-to-diagnose latency spikes. Aggressive right-sizing that ignores extreme workload spikes takes a cost-saving measure and immediately turns it into a self-inflicted performance degradation. This quadrant matrix maps out the strategy. For high-scale, resource-rich teams, pre-production cross-architecture benchmarking is non-negotiable. At that scale, the cost of inefficiencies compounds massively. Rapid iteration startups lacking the time to benchmark should lean heavily on the flexibility of compute savings plans, provided they carefully right-size their instances prior to committing. But regardless of your scale, never give in to the temptation of trimming the cloud bill by cutting your system observability and monitoring tools. Cutting observability destroys your feedback loop. Without that data, you have no way to know if an architecture migration caused a fatal latency regression. Treating system visibility as overhead might save a fraction of the budget today, but it guarantees your next catastrophic cost surprise will arrive with zero data to diagnose it.